Friends, this is the fourth and final video for the completion of answers of the NEEP 2021 practice exam in physics. This is questions 11 till 20. Question 11 is right here. This is a momentum question. As soon as you see a collision, it's almost certainly going to be a momentum question. The only other thing it might be is about impulse. It's nearly always momentum though. And sure enough, this one is as well. There are two moving objects heading in the same direction in this case, but one is going to catch up and hit the other one. Right? They both have a certain amount of momentum before. They're going to clip together after they hit, and the question is, what's the velocity of the both of them together after the collision? This is a very standard question. This should be a very quick one. It's 3 marks. You should be able to do this very quickly. Momentum is m times v, and the total momentum of the whole system beforehand is going to equal the total momentum of the whole system afterwards. So this is the momentum before, m times v for that, n times v for that equals m times v for the whole thing. You don't know v, so you're solving that to get the velocity, and that's how it's done. The only way this gets more complicated is if there are 2 directions, in which case you just have to take one as positive and one as negative, and be careful with putting in the positives and multiplying the negatives correctly when they get into the calculations. And if you get a negative answer, it just means it's going in the negative direction. All right, easy question. Okay, question 12, and I'm assuming that you can read your own copy if you can't read this one. A spacecraft of mass 5 million kilograms is traveling from Earth to a star system that is 10.2 light years from Earth as measured by scientists on Earth. Spacecraft travels at 0.75 times the speed of light, so the Lorentz factor is 1.51 directly at the star system. According to scientists on Earth, the trip is going to take 13.6 years. Will the measuring instruments on the spacecraft record a greater, equal, or lesser time than 13.6 years? Provide an explanation for your answer. Do not provide calculations. So please don't provide calculations here. They won't read them. Only an explanation will do. Okay, so here's the explanation. From the perspective of the spacecraft, because the spacecraft is moving in relative to the outside world, or the outside universe in this case, the outside universe is going to look constricted. It's going to look contracted, right? Length gets contracted. So when you look out the window of the spaceship, the distances all look shorter. And because the distances are measured to be shorter, but the speed at which you're traveling is measured to be correct, distance over time gets you a smaller amount of time that it's going to take you to get there. There is another way to answer that. Excuse me. The fact that the time measured by the people on the spacecraft is actually less time, is actually dilated time compared with the time on Earth, means that they will experience less time on the spacecraft during that trip than people on Earth will experience while they're watching that trip. So either way, according to the people on the craft, the whole trip's going to take less time. Part B, find the kinetic energy of the spacecraft as it travels to the star system. It's a relativistic speed, 0.75 times the speed of light. So you need to use relativistic kinetic energy. Gamma minus 1 times mc squared. Easy. Question 13. Excuse me. A progressive transverse wave, again, that's a transverse wave that's going somewhere. It's not a standing wave. It's actually being seen to move. For a particular instance in time, it's literally been photographed as measured by its position. The wave moves to the right at 6 meters per second, okay? All right, that's its position in meters, fair enough. So it goes from there to there in 1 second. So that spot, 1 second from now, is going to be up here. Okay, what is the period of the wave? Now, the period, the definition of the period is how long it takes for one wave to go past. So if the wave is going from there to there in 1 second, that is one wave. That is 2 waves. So 2 waves are going to go past in 1 second, which means the frequency is 2. The frequency is how many waves go past in 1 second. Period is the opposite. It's the inverse of that. It's how many seconds it takes to go to have one wave go past. So, excuse me, if it goes that far, if two waves go past in a second, right, then one wave goes past in half a second. So the period is half a second. Now the answer for part B is actually incorrect on the NEAP solutions. It's not so much incorrect, but it's just not specifically accurate. It says on figure 14, sketch the position of one cycle of the wave. 0.25 seconds later than the instant shown. And on the answer, they've just done it from one end to the other. They've done like 2 cycles or 3 cycles. Right, so one cycle is just one full wave. All right, so a quarter of a second. It's going 6 meters a second. So if it goes 6 meters in 1 second, it's going to go 1.5 meters in a quarter of a second. So that distance there is 1.5 meters, right? There's the 1.5 between the 1 and the 2. So you basically have to draw that wave starting there, which is roughly this. There you go. So not counting that initial red part that I was just marking something with, that is one cycle of that wave a quarter of a second later. That is where the beginning of the wave is going to be in a quarter of 1 second. Question 14. Sorry, I'm just going to write this a little bit. There you go, question 14. Okay, 2 loudspeakers, L1 and L2, are playing a single note simultaneously using the same power output. That just tells you that they both push out a crest and a trough of a wave at the same time in the same direction. All right. Zara is standing over there, a distance of A away from one of them and B away from the other. You don't know what those distances are just yet, and now you do. There's a table down here to tell you. She's 5.4 meters away from A, 3.8 from B. The speed of sound in air is 340 meters per second. Okay. At a particular time, these guys are playing a note of frequency 850 hertz simultaneously. Basically, what is she going to hear? Is she going to hear the note as loud as it's coming out of the speakers? Is it going to be louder? Is it going to be less loud? And why? Explain it. Okay. So this is all about, let me just get this question out of the way for a minute. This is all about interference. We've done this with 2 slits and a wave coming through. This one is just a situation where there are 2 speakers and waves coming out. Right. And you've seen these diffraction patterns form. And you know that over here where they're heading, there is a point there where that's going to be equally loud because you're going to get constructive interference. And there is another point where you're going to get constructive interference, constructive. There are various points along this wall where if you stood there, it would be louder than it would be if you were just standing around here somewhere, even though you're closer to the speakers here, because you're getting constructive interference, bigger waves. Right? That happens when the path difference, when the difference between the length of that journey and the length of that journey is a whole number of wavelengths. Right? So that first one will be 1 wavelength difference, 2, 3, etc. In between those spots, the path difference is either half a wavelength or half a wavelength plus a whole number, like a half, 1.5, 2.5, 3.5, etc. Right? And at those places, you get destructive interference and you don't hear anything, or you barely hear anything. You will still hear something in reality because this is an enclosed room and sound is also bouncing off the walls and getting you in the ear the other way. So you wouldn't hear silence, but you'd certainly hear less volume. Okay, so we've got to figure out whether Zara is there, or indeed somewhere else. So let's do it. Knowing the wavelength is the key here. So we know the frequency, we know the velocity, we're going to find the wavelength, okay? So the wavelength, excuse me, V equals F lambda. I've just turned it around. And that equals 340 divided by 850. And so we're going to find the wavelength of this waveform. And that comes to 0.4 meters. Okay, so here are the distances. If that is a whole number multiple, if the difference between those two numbers, pardon me, is a whole number multiple of 0.4, she is standing in a place where there's constructive interference, right? If it's 0.2, which would be half a wavelength, plus a whole number of 0.4s, then she would be in a place of destructive interference. Turns out that the difference between those happens to be 1.6, which is 4 of those, right? So you say the path difference equals 4 wavelengths, therefore constructive interference, therefore Zara hears more volume. 1 mark, 2 marks, 3 marks, 4 marks, that's pretty much how it's going. So part B, Zara moves to a new position so that distance A is now 6 meters. She's still closer to speaker L2 than she is to speaker L1, right? So that's the one from A. The note played in the speakers changes to a note of wavelength 0.75 meters. Zara is now barely able to hear any sound, so she's in a position of destructive interference. Right? Determine a possible value for distance B at her new position. Show your working. All right, I'm just going to get back to the diagram here. So let's say she's at that point there where we have destructive interference. I'm just going to put a few labels on this. L1 and L2. And the distance A, which was from L1, I'm just going to double check that I don't get this diagram wrong. Yep, distance A from L1 is now 6 meters. The wavelength that's coming out is 0.75 meters. So if she's there at point, I'm just going to call that point C. At point C, the path difference is going to be a half of the wavelength. Right? It's going to be a half of 0.75 meters. That would help if I actually zoomed out a little bit so you can see what I'm writing. A half of 0.75 meters, which is 0.375 meters. Okay, so the question says determine a possible value for distance B, which is this one, that other orange. Okay, well, one possible value is 6 meters minus 0.375, right? That would be what I would do. They said give one possible value. Don't worry about getting a difficult one. Just get the easiest one. If the path difference is half a wavelength, it's going to be destructive interference. And because of the fact that she is feeling or hearing almost nothing, she is in a position of destructive interference. So a possible value for B is 6 minus 0.375. Which is, what is that? That is 5.625, I think. Yes, it is. Meters. All right. Okay, question 15. I'm going to go through this with a bit of a diagram here. The question says this. It says, explain why the term resonant frequencies is used to refer to musical notes produced by plucking a guitar string. All right, so here's one guitar string, unplucked. When you pluck a guitar string, when you pluck anything that can be plucked and is flexible enough, if you hit it there with your thumb, you end up sending waves from that spot out. It's a bit like when you slap the surface of water, you get a circular wave that sort of radiates out from the spot that you slapped it, right? A string is not a two-dimensional plane like the surface of water. It's a one-dimensional thing, so you get one wave going to the left and one wave going to the right. But they travel along the wave. And when they hit the end, they reflect and they come back. And when they occupy the same place, they go through each other and they keep on going, bouncing back and forth and back and forth. They don't travel at the speed of sound. Right? The
secondary wave that these things hit the air with, because they're also going up and down, right? Excuse me. That travels at the speed of sound, right? As these waves bounce along and travel up and down the string, they are knocking air particles out of their own way, and those air particles hit other air particles, and they hit other air particles, and that wave in the air goes at the speed of sound. These guys, I don't know how fast they go, but they wouldn't be going at the speed of sound. However, they're not the notes that you hear. The ones that literally you could see traveling in a slow motion video, they are not the ones you hear. They don't make a note. Right? They're not loud enough. Just hold on a second. Sorry, I interrupted that program to rescue a cat from another cat. Anyway, what was I doing? Okay. These waves travel along the string, but they don't make the note. There is one wave that actually is so big that only half of it fits across the whole string. This is the one, right? So that's where the straight string was. But there is also a big wave there. There are several different sized waves that travel up and down the string at the same time, and they go right through each other, and it looks very complicated if you look at a vibrating guitar string in slow motion, because they're all adding their amplitudes together, so you can't really make sense of it. But the note you hear corresponds to this wave here. This is the biggest one that actually fits as a standing wave. Right? There's a node there where the string is stuck, right? And a node there, right? The stock and the head. Okay, that wave, that is only half a wave, of course, so the wavelength of this wave would be way out there, out beyond, like that. Okay. This is the note that you hear. If that is a C, you're going to hear a C. You're going to make all these other little waves as well that are going to go dancing along that string. But the one wave that does that is the one that you hear. It resonates. It's louder. It looks like it's jogging on the spot rather than traveling from one end to the other. It is actually still traveling from one end to the other. Studies have shown that this is happening, but it doesn't look that way. And because it bodily pushes the air so much better than these guys do, right? Because it's just going whump to along the whole length of the string. That's the one you hear. That's the note that dominates everything. Now there are other notes that are also created by standing waves, and each of them has the characteristic that there is a node at each end. In this particular case, there's a node in there as well. That part of the string, if you could only get this note going, get this wave going, that part of the string wouldn't move. This whole thing would be going like this. So again, it looks like it's jogging on the spot, and because it's not really going sideways, right, the physical ramification of it is the string goes up and down and up and down. It whacks a lot more air than these traveling waves, and again, that contributes significantly to the sound. That is the note that you hear. These smaller ones that are also standing waves, excuse me, because they're resonating, they also contribute to the sound, and they're the sort of things that make it sound like a guitar note, right, instead of a piano note or instead of a saxophone note or something, right? That makes it a C. These other ones and their relative strengths compared to the fundamental note. Maybe I should not use that particular finger to point to make the fundamental note. They actually give the note its characteristic sound. They make it sound like a guitar instead of a flute or something. And that property of dancing on the string without going left to right and left to right is called resonating. Right? That property of being a standing wave and fitting exactly into the space that the string has allowed you to vibrate in, that's resonating. This is resonating, this one resonates, this one resonates, they don't. Now I have just given you a plain English description of what resonating is and standing waves and so forth. To answer the question, I think the solution that was given by Neep is a fantastic solution. It's really well said, but I just thought I would add to this with a bit of a plain English explanation of what resonance actually is. All right, let me just zoom this out. This is question 16, and this involves Snell's law, and this is not the easiest question in the world. You can get a little bit lost in this one. All right, let me show you the picture. You've also got it yourself. A ray of green light I'm not going to draw on this. A ray of green light is heading from water into sapphire. Sapphire has a higher refractive index than water, 1.77 versus 1.33, so it does the same sort of thing as something that's going into water, right? The light refracts deeper, right, so that the angle of refraction is less than the angle of incidence. Then it bounces off, excuse me, off the surface here, right? And it says, at a specific angle theta, the transmitted ray of green light only just reflects at the sapphire air surface. So that's water, sapphire, air. Right? So it actually doesn't do this, right? You know, it just reflects. If it was any, they're trying to tell you that that's the critical angle, right, for this juncture, right? That any bigger angle, and we would have got the light getting out into the air, right? But we've just gone to the critical angle, so that there. Let me make less of a mess of this than I'm making. That angle there is the critical angle for that boundary between sapphire and air. Now, they haven't told us what it is yet, but we're going to figure it out. So the question is determine the size of the angle theta, the original one. So we have to sort of work backwards here. All right. So I'm going to show you how we're going to do this. The critical angle is the angle of incidence for which the angle of refraction is actually 90 degrees, right? So there's the normal, and that is the angle of refraction. Any further past the critical angle and you just get reflection, total internal reflection, which is what they drew on their diagram before I covered it all up with my crayons. All right, so how do you do this? So here's the plan, Stan. We are going to use the formula for critical angle. We're going to use Snell's law to work this backwards and find out what that angle is. We know that's 90 degrees. Right? We know both refractive indices of this barrier, so we can find out that first angle. That angle is also this angle. Right? The burgundy angle is the orange angle, right? Because they're alternate angles, right? Two parallel lines are diagonal. So then we're going to work backwards here, and we're going to know what that angle is, and we know these two refractive indexes, and we're going to find out that missing angle. So we're just going to do this sort of Snell's law backwards twice, right? So here is Snell's law. Well worth knowing this one well. Right? There's nearly always a Snell's law question, and they're always pretty straightforward to do, but you can get lost in it a little bit. So I haven't put any subscripts on this at the moment. Snell's law goes like this. If that's 1 and 2, then that's 1 and 2 as well. They're the same, but these guys are upside down. The refractive indices are the other way around, 2 and 1. Or if you go A and B, or top and bottom, or first and second, or initial and a refractive, or whatever. But that's Snell's law, and we're going to use it twice here. Okay, so firstly, I'm going to start labeling or naming some of these angles, because again, like I keep telling you, you are welcome to draw and label angles. So I'm going to call that big pink one angle C. I'm going to call that orange one angle D. Doesn't matter what you're calling, you can call them anything you want. Okay, so finding angle C first. So in a multi-step question, tell the person marking it what you're doing, right? Setting out helps a lot. Right? So I'm going to say, sorry, I'm going to get this around the other way because I'm right-handed. All right. That's a little better. Okay, so firstly, find angle C. Excuse me. So the initial, so this is medium 1 and this is medium 2 for this little part, okay? So we've got, let's see. I'm going to put this upside down. Or am I? No, I'm not going to. I'm going to leave it the way it is. So N2 on N1. Okay. 1 over 1.77 equals. sine theta 1 by sine theta 2. Sine of theta 1 is what we're trying to find, right? Sine of angle C, in this case, divided by the sine of 90, and the sine of 90 equals 1. Solve that for sine C, go 1 divided by 1.77, inverse sine, and you get that angle C is 34.4 degrees. Okay, first part done. Now we're going to find, so therefore, angle D is 34.4 degrees, right? Because of that alternative angles rule. Right? So now we're finding theta. So again, where there's a multi-step process, tell people what you're doing. It really helps. It also helps tell you what the hell you're doing, because you can sometimes forget what you're even up to. Okay, we're now finding theta. So we use Snell's law again for these two, right? So 1, 2. So N2 is going to be the 1.77. N1 is going to be the 1.33 of water. Sine and sine. N2, N1, but it's sine 1 and sine 2, right? So the sine of theta, that's the one we're trying to find, divided by the sine of 34.4. And you solve that, and you end up getting theta. It turns out to be 48.8 degrees. That's how you do it. That's quite a clever question, actually. You have to literally do things backwards. You have to start at the end and work your way back to the beginning. That's one of those questions you can very easily get lost in. Hence, the setting out really helps you as well as the person trying to market. Yeah, remember when I said I wasn't going to draw on that previous diagram? Here's why. And then I drew all over it, and I'm regretting it now. Doesn't matter, because we don't particularly need this diagram. You know what the photoelectric effect is. They're just drawing a picture of the photoelectric effect happening. Excuse me. So let's read this thing. In a photoelectric effect experiment, light is shone onto a metal cathode of a photocell as shown in the figure. Yep. Okay, the data recorded is shown in table 1. Intensity and photocurrent were qualitatively recorded. Okay, so they didn't measure it, they just measured it as low and high or big or small or whatever. Okay, so color and wavelength of the light that they shone on something. The intensity was either low or high, or right? And they measured the stopping voltage and they measured the photocurrent. Right? These two were set, so these were independent variables and these were dependent variables. Right. I'm going to read the question to you. We're going to keep this on, but I'm going to read the question because it's on the other side. Does any of the data above conflict with the wave model of light? Explain your answer. 4 marks. Okay. Answer is yes, it does. Okay, so you need to know what the wave model of light says. And I've gone through this in a reasonable amount of detail before, so I'm not going to sort of write it all out for you again. But the wave model of light tells you, amongst other things, that increasing the intensity of light should have increased the voltage or the stopping voltage of any photocurrent, right? And it didn't. Right? It didn't when there was nothing. It didn't when there was something, and it didn't when there was even more. Right? So the stopping voltage was unaffected by having low, high, same as trial 1, which is low and that's high, and that's low and that's high. If the only thing they did was change the intensity of the light, it did not change how much energy the photoelectrons had. The stopping voltage was the same. All right. So wave model says that should have been higher for a more intense light. Right. The evidence didn't prove that, or proved it to be wrong. So that's one thing. Now the other thing about this that contradicts with the wave model is that any light should be able to create a photocurrent. It doesn't matter how much light you use. If you use light of a lower intensity or a longer wavelength, and therefore of less energy, you'll just have to wait a little bit longer for the photocurrent to come along, right? Because the wave model says that no matter what sort of waveform you've got, it's a continuous wave. So if your electron is down here and it's receiving a low energy wave, it just has to wait for a little bit more of it, right? It's like filling a fuel tank with a slower hose, right? It just has to wait a little bit longer for all of this to get in there and add up to the energy that it needs to jump, right? In reality, that doesn't happen, of course, because we now know that light doesn't come like that. It comes like this in little photons, and one electron gets one photon, and the energy of that one photon has to be able to do the whole job, or nothing happens, right? So wave model predicts that there would always have been a photocurrent here, right? And for the first trial, there just wasn't. No matter how high the intensity of that light was, you didn't get anything happening. Part B down here, it says, determine the work function of the metal in the metal cathode. Show your working. Okay, let me show you this. Formula goes like this. It's basically a version of conservation of energy. Energy in, that's the energy that's in a photon, E equals HF, right? And it all goes into the electron, excuse me, and it turns into the work function, which is the energy that it takes to release the electron from the metal in the first place, plus the kinetic energy that the electron gets as well, right? This is the energy that goes into the electron, and this is what the electron does with it, right? It escapes and it moves. Right? Now, in the case of energy measured in electron volts, excuse me, that is just the stopping voltage in electron volts. Right? So if you do this in electron volts, in other words, if you use the electron volt version of Planck's constant, which is that 4.14 by 10 to the minus 15, I think it is, right? Then this just works, right? And it says calculate the work function. Well, you've got the frequency of the light that was given. Pick any row of the table. You've got the frequency of light given. You've got Planck's constant, and you've got the stopping voltage. So all you have to do is plug those three numbers in and solve to get that. There are variations on doing this. I think the answer booklet gave you like 4 different methods for doing this, but this is the way to go, right? They also gave you this formula a little bit differently. They did stopping voltage equals HF minus W, but it's the same thing, right? I just think the way that this is written makes a little bit more sense, because that's energy in and that's energy out, or that's energy supplied and that's energy used, and they equal to each other. Right? All right. So that's actually a reasonably easy question for 3 marks if you know how to do it, and if you make sure you've got the units of everything right. Electron volts, that's the Planck's constant to use. All right. Okay, question 18. Excuse me. An electron is accelerated from rest to a particular speed by an electric field with a potential difference of 10,000 volts. A, determine the de Broglie wavelength of the electron accelerated by the 10,000 volts. Show your working. Okie dokie, let's do it. Okay, the given answers, the solutions, gives you one way to do this, and they've sort of overdone the algebra a little bit. But it is a bit of a painful question. It's just a boring mathematical physics question, this one. There's no real interest in it. So I'm just going to get through it. Here's how I would do it. Right? This is a little bit different to the way the book actually does it, to the way NEAP does it. Right? But so the formula for the de Broglie wavelength goes like this. Right? Lambda equals h on mv. Right? Mass of an electron, velocity of an electron, Planck's constant. We don't have the velocity of the electron. However, we do know that the energy that's been given to it is 10,000 electron volts, right? 10,000 volts, hit an electron with it, you get 10,000 electron volts. Okay, convert that to joules. Right? Divide that by, multiply that by 1.6 by 10 to the minus 19. That's the conversion factor. And you get that is 1.6 by 10 to the minus 15 joules. Okay, that will be the kinetic energy of the electron having gone through 10,000 volts, having been accelerated by 10,000 volts. So in other words, that equals a half mv squared. Right. Now you can solve this for v. right? And you end up getting a final velocity of 5.93 by 10 to the 7 meters per second. So again, you're putting the electron's mass in there. It's 9.11 by 10 to the minus 31. It's also on the data sheet, right? And you'll end up getting that for the velocity. So now you can use this. So you go back to the de Broglie wavelength and you end up getting 6.63 by 10 to the minus 34. That's h over 9.11 by 10 to the minus 31 times 5.93 by 10 to the 7. And you do all of that and you end up getting 1.23 by 10 to the minus 11 meters. That is the de Broglie wavelength of that particular electron that's been accelerated by 10,000 volts. There is another way to do it. NEAP shows you another way to do it. I think that one's a little bit cleaner. It's just me. Now, having done that, part B tells you to calculate the momentum of a photon that has the same wavelength as the de Broglie wavelength of the electron in part A. Show you working. Okay, let's do that. Photon momentum, here's the formula for photon momentum. Momentum is h divided by lambda. You just got that. So this should be pretty well straightforward. All right. Comes to 5.4 by 10 to the minus 23 kilogram meters per second. Right, question 19 is out of 3 marks. It's got half a page of lines for you to fill. You don't have to fill them, of course. You just have to answer the question, as always. The length doesn't particularly matter, as long as you've got the criteria right. All right, so it says explain how the emission spectrum for hydrogen, which they've given you here, provides evidence that electrons have wave-like properties. Okay, there's a bit of sort of joining of dots here, right? The emissions, firstly, tell them what an emission spectrum is. What are we looking at there, right? This is a spectrum that's created by energizing hydrogen, excuse me, by either typically electrocuting it, right, but giving hydrogen atoms energy in their gaseous phase. And they re-release that energy as photons of light, right? But we only get particular frequencies, particular wavelengths of light, right? So that's the first point. You only get particular wavelengths of light. All of the other black stuff is missing from hydrogen. Now that means the energy of these electrons must be of a specific value as well. You never ever get a line there, for example, right? It never happens. It's always, always, always these. So there are only particular levels of energy that electrons can occupy, right? And there are specific differences between the two bands, and that's why you get only specific wavelengths. And the explanation for why they have that is because they exist as standing waves, or they at least travel around in their allotted regions around the nucleus of an atom as standing waves. It's been mathematically shown that they, if that's the nucleus, that they exist in positions where a whole number of their own de Broglie wavelength will make one lap of their particular little domain, whether it's a 1s orbital or a 2p orbital or whatever, for the chemists. So you have to just join those dots. You have to firstly say that those guys are representing specific wavelengths, and that implies that electrons have specific amounts of energy and that they cannot have others, which implies that there are places around the nucleus that they can't go. Right? There are only specific regions that they can or can't orbit, and there are very few of them as well. And then you need to give the reason that there are only specific orbits available, and it's linked to the wave structure. If they weren't traveling in waves, if they didn't have a wave nature to their movement around the nucleus, they wouldn't have this problem and they'd be able to fly anywhere. However, they do have a wave nature, so they have to fit in where there's a whole number of waves in one orbit. That's the final dot you have to join. Question 20, this is the final question of the test, and this is where you discover that this is a very cruel exam. Because when you turn over and you go, oh, thank God, it's the last question, I'm nearly done, and then you say it's worth 16 marks, you want to sort of kill somebody. All right, so let's just get into this 1 mark at a time.
All right. We know this situation reasonably well. We've actually done this as an assessment. Laser light shining through something that's going to diffract it, and it makes a diffraction pattern. It's actually shining at a hair, right? Because there are three ways that you can get light to diffract. You can either shine it through one slit, it goes through there and diffracts, right? Or you can shine it through two, and it'll go through there and cause a diffraction pattern, right? All of these cause a diffraction pattern, right? You get the most marked diffraction pattern when it's a double slit experiment, or you can shine it at something that's really tiny as well, and it will diffract just past it. Right? And it'll also give a diffraction pattern, give a diffraction pattern further off on a projector screen. Right? So that's what's going on in this case. It doesn't really matter why it's diffracting. All you need to understand is that it is diffracting and it is making an interference pattern as shown. All right. The mechanism isn't that important. This is what we're worried about. Okay, so let's get into this question. They've reminded you what all of these things stand for. That's pretty handy. Okay. The students become aware that the pattern observed on the screen would be identical to the pattern created when a laser is fired at two very small slits. Well, there you go. That are a distance apart equal to the width of the hair. Right. So if that width of the hair was the same as, and in this case it isn't, was the same as that distance between the two slots, you'd get the same diffraction pattern. Right. Same sizing, same delta X. All right. The experiment was repeated with a number of hairs of different widths. The width of each hair is determined using a microscope measuring system. Right? The length, the L, the distance from the hair to the board, to the projection, is 5.5 meters for each hair used. Explain using physics principles the effect of increasing the width of the hair on the pattern produced on the screen. Well, the physics principle is the formula. All right, delta X, excuse me, equals, just had to get a cat off me, lambda L on D. There's your physics principle. Okay. So, for example, increasing the width of the hair without doing anything else, if you increase that number, if the bottom number of a fraction gets bigger and the top stays the same, it ends up making this smaller, right? So increasing the width of the hair without changing anything else is going to make delta X smaller, which means it's going to make the gap between these bright spots less. So the pattern's going to contract. Excuse me. Part B, identify the independent and dependent variables in this experiment. Give your reasoning. Okay, what did they change? What did they measure? There are 12-year-olds at Wrighton that could answer this question, so you'd better get this one right. Okay. They changed. The experiment is repeated with a number of hairs of different widths. So the independent variable is the width of the hair. That's what they're changing, right? The width of each hair is determined, blah, blah, blah. Okay. And what did they measure? They measured delta X. They measured what was changing in response to their change of width of hair, okay? They changed that, it changed this, and they measured it. So independent variable is the width of the hair. Dependent variable is the distance between adjacent bright bands on the screen that they were projecting it. Okay. Next question. The results are shown in table 2. The heading for the last column shows the uncertainty for the quantity. Okay. Calculate the values of 1 on D and write them in the spaces provided in table 2. There you go. Express them to the correct number of significant figures. Do not determine the uncertainties. Right? Just write the values in there. All right. The correct number of significant figures is 2 because you're going to go 1 over that, and that's got 2 significant figures. In every single case, they've got 2 significant figures. So you're just going to go that 1 on X, that 1 on X, okay? And it ends up being 4, 3, 2, 1.3, and 1 by 10 to the 4. Okay, so that's a reasonably easy 2 marks. Plot a graph. This is why it's worth 16 marks. There's so much to do. It's all reasonably easy, but it's just a long finish to a test. Okay, plotting a graph of delta x on the y-axis and 1 on d, excuse me, for the x-axis. On your graph, and you have to do all of this to get all the marks, right? Include an appropriate scale for the y-axis and include an appropriate scale for the x-axis. Okay. So you're doing delta x on the y-axis. So you look at the table, you know how to do this. I won't even bother, right? Draw a straight line of best fit. They're telling you it should be a straight line. So if you plot the points and they're all higgledy-piggledy, you've done something wrong. They're going to make a pretty straight line, all right? And include uncertainty bars on the x-axis only, right? The x-axis is 1 on d here, and they gave you the uncertainty. So you've got to put error bars that are plus and minus 0.1. So either side of the dot, you've got to go 0.1 that way, 0.1 that way, right, on your according to your own scale that you decided. All right. It's a bit of work, it's a bit of a rigmarole, but it's only going to take you like 3 or 4 minutes and you're going to get 6 marks for it. Right. Okay. And the final question. Use the straight line of best fit drawn in part D. Did it tell you to draw a line of best fit? Yes, it did. Sorry. Use the straight line drawn to find the value of the wavelength of the laser light. Okay. Well, the way to do this, the gradient is, of course, the rise over the run, which is delta x divided by 1 on d. Right, now, let me get a fresh piece of paper. Sorry, guys, I'm running out here. Running out of space, not paper. Okay. So the gradient of that graph, is rise over the run. And of course, dividing by 1 on d means multiplying by d, right? So it equals delta x d. That's the gradient. All right. But delta x also equals lambda L on d. And therefore, delta xd equals lambda L. And therefore, delta xd on L equals the wavelengths. So that's what you're going to do. That is the gradient. You've just got to divide it by the length, which was 5.5 meters, I think, from memory. You just look it up. Right? And that's the wavelength. So that's how you finished that last one off. Right? Fairly straightforward. Make sure you've got the units right and you're done. Okay, my friends, that is every question explained of the 2021 NEEP trial exam. Thank you very much.